11, and this is section 4.3 on eigenvalues. And so they tell me that A is the matrix 1, 0, 0, 0, 0, 1, 0, 0, 1, 1, 3, 0, negative 2, 1, 2, negative 1. And there are some different parts. So part A said, hey, compute the characteristic polynomial. So characteristic polynomial, of course, is the determinant of, well, right, it's the determinant of A minus lambda I, which is the determinant of, let's see, it's 1 minus lambda 0, 0, 0, 0, 1 minus lambda 0, 0, 1, 1, 3 minus lambda 0, negative 2, 1, 2, negative 1 minus lambda, right? And I claim that that equals 1 minus lambda times another 1 minus lambda times 3 minus lambda times negative 1 minus lambda. That is the value of the determinant. Do you see how I know that? This is a, go ahead. Yes. That doesn't always work, but that works if you have what's called a triangular matrix. I mean, how do I prove that it's going to work? Look, let's expand across the top row. So it's 1 minus lambda times the determinant of this submatrix, right? See that? But then expand across that top row. So now it's 1 minus lambda times 1 minus lambda times the determinant of that matrix. And so you can see, kind of just continue going across the rows and it's going to work. Does that make sense? For an upper triangular, I think you would do the columns and it works. So that's part A. I mean, I guess I could multiply this out and I'd get some fourth. Oh, actually, if you, again, if you went along the wrong column, this is a hard problem, right? So yeah, that's a nice little property to know. Okay, part B asks, can we find the eigenvalues? Well, yeah, that's easy once you have this. What are the eigenvalues? Do you have that for me, Mitchell?
1.
Yep.
3, negative 1.
That's right. And I want to talk about multiplicity, because this was an idea we hit before break, but I think it's worth reviewing again. What can you tell me about multiplicity?
The algebraic multiplicity of 1 is 2.
That's right. This has algebraic multiplicity 2, because there's a 2 there. The other ones are algebraic multiplicity 1. And then you might remember that we learned that the geometric multiplicity is always less than or equal to the algebraic multiplicity. Do you remember what geometric multiplicity means?
The dimension of the eigenspace.
That's right. This is the dimension of E lambda, right? So part C said find a basis for each eigenspace, and this is what you said you wanted help with, right? Should I do E1 to start? Because that's kind of the most interesting one.
That's the one that I actually got wrong. So
Okay, so let's do E1. E1, what we're supposed to do is actually find a basis for E1. That's what we're really supposed to do. Okay? And then I think they also want a basis for E3 and E negative 1, but I'll just do E1. All right, so here's what we do. When we want to find a basis for E1, and again, I'm going back to the computation from before break. So we've seen this many times, but it's worth another repeat. Ready? Here we go. AX equals lambda x. So AX minus lambda x equals 0. So AX minus lambda IX equals 0. Then what?
Factor out the x.
Yes, A minus lambda IX equals 0. So I have a matrix times x is 0. And so what I'm really doing when I say E1, E1 is the null space of A minus 1 times I. That's what I'm really doing, is I'm looking at the null space of A minus 1 times I. Okay, so let's look at that. So let's see. When I say the null space of, well, what's A minus 1I? Well, A is up above, right? It was that matrix. So A minus 1I would be the matrix. Let me just change those diagonal entries. They would become 0, 0, 2, and negative 2, right? Everything else stays the same, so I'll leave everything else the same. So we have a bunch of zeros up top. Down bottom here, I guess this is a 0. And then I have 1, 1 in the third row, and then I have negative 2, 1, and 2 in the fourth row. And this is a 0. Okay, so the null space of that matrix is what I want to think about. And I don't know if you guys are still doing this or not. I used to draw the dotted line and put the zeros here. We don't have to, right? But, I mean, remember, you can switch rows. So maybe I'll write it this way. 1, 1, 2, 0, negative 2, 1, 2, 0, and then a row of zeros, and a row of zeros.
The fourth entry in the second.
Oh, that's a negative 2. Thank you. Now what? Probably do 2 row 1 plus row 2 is the new row 2, right? May as well row echelon form this thing. So we're looking at the null space of this 4 by 4 matrix. 1, 1, 2, 0. Let's see. 2 times row 1, so this becomes a 0. 2 plus 1 is 3. 2 times 2 is 4 plus 2 is 6. And then 0 plus negative 2 is negative 2. And then these are all zeros. Is that in row echelon form now? I think so, right? Okay. How many free variables are there? 2. There are 2 free variables. Right? So I'll set x3 equal to s, and I'll set x4 equal to t. So then I can write the equations. After I do that setting, I can say that the top equation says x1 plus x2 plus 2s equals 0. And what's the second equation say?
3x2 plus 6x 3 minus 2x 4,
There it is. Yep. So x1 plus x2 plus 2s is 0, and 3x2 plus 6s minus 2t equals 0. So now, here's how I do this now. See that equation there? I can solve for x2. I can say that x2 is going to equal, well, 3x2 would equal 2t, how about I write it as negative 6s plus 2t, right? And so x2 would be negative 2s plus 2/3 t. Is that okay? And now I'll go back to the top equation, right? And let's rewrite that. We have x1 plus, and then x2 is negative 2s plus 2/3 t, and then plus 2s equals 0. Okay, so if you simplify, you get x1 is equal to negative 2/3 t. With me? Okay. So, continuing. Things that are in the null space, what do they look like? Well, x1 has to look like this. Negative 2/3 t. x2 has to look like this. Negative 2s plus 2/3 t. x3 would be s, and x4 would be t. Those were the two free variables that we started with. Are you with me? We can also express this in the following way. S times a vector plus t times a vector. Maybe I should be using, again, some books use brackets, some books use parentheses. Doesn't really matter. So what are the vectors? I guess it would be 0, negative 2. Well, s is 1 here. 1, 0. Okay? And then what would the second one be? Negative 2/3, positive 2/3, 0 and 1. Yeah? So I'm almost done. I'm almost out of room, too. You're right, these take a lot of work. A basis for E1 is given by, well, I'll take that first vector. So let's use 0, negative 2, 1, 0. But I'll tell you what, if it were me for the second vector, instead of using the fractions, I would multiply the second vector by 3 to get rid of all the fractions. And I would use this vector. Negative 2, and then it'd be positive 2, 0, 3. Because you just multiply, make t 1/3 of the size of what you would have made it, and you can get back any point you want. So what did we just learn about this matrix? We learned, oh, that's what they said for part D. The geometric multiplicity is also what in this case? 2. Right? So in this case, so part D was that basically asking, what's the geometric multiplicity? So the only question was this one. This one is also the geometric multiplicity also. And for here, both multiplicities are 1, and for here, both multiplicities are 1. Yep.
The book had E1 equal to the span of negative 2, 0, 1, 3, negative 2, 2, 0, 3.
Okay.
So that's why I was so confused on that one.
Well, so that's interesting, right? The book gave a different basis for the same subspace. Now why? They may have solved the system of equations differently. All I have to do, guys, is switch these two, and I'll have a different solution, and I'll come up with different basis vectors, right? I mean, I could have given you these two. I just didn't want fractions. So I guess this is interesting. The basis is not unique. There are infinitely many bases. What is unique? The geometric multiplicity, the number of vectors in the basis is unique. Even going back to 2 dimensions, okay? And I showed this the very first day of class. We have the standard basis. We called it I and J, right? So 1, 0 and 0, 1, right? That's a really nice basis for R2. Or if you do R3, it's I, J, and K. But you could also get any point in R2 by taking, I don't know, 1, 0 and 1, 1. And we showed the first day of class how you could just make your graph paper a bunch of parallelograms. Remember that? That's kind of cool also. All right. Next. So this is section 2.3, problem 22, which we're going to come back to several times over the next couple weeks. It's a statement that's dear to my heart here. If V, we want to prove this. Prove. If V is and I'm going to continue to use my my shorthand, an eigenvector of A with corresponding eigenvalue lambda, and C is a scalar you could try and do this too, Mitchell, if you want. Show that V is an eigenvector of A minus Ci with corresponding eigenvalue lambda minus C. And so what we've been doing all year long is saying, well, okay, if I'm supposed to do a proof and if I'm successful, this is going to be the last statement, right? So let me write it at the bottom of the paper. I mean, this may take some work. So here I go. V is an eigenvector of A minus Ci with corresponding eigenvalue lambda minus C. And I hope that, oh, you can't see that. I hope that that shorthand is okay for you guys. Let me zoom out a little bit. Okay. And so as I look at this problem, I also want to take the given information, right? So what are we given? Well, we're given this. V is an eigenvalue of A with corresponding eigenvalue lambda. And what I want to do is I want to take that statement, I want to unpack it, right? That's what I called it. So what would you write? How do you translate that underlined statement there? V is an eigenvalue of A with corresponding eigenvalue lambda. Yeah, we usually write it this way, but yep. AV equals lambda V. That's the given. Okay? But what you do, when you do proofs, quite often we work backwards. And that's where I said, go to the bottom here and let's unpack this. So Mitchell, your turn. Can you unpack that? Can you translate that into a statement? So we're going to write, yeah, A minus Ci in parentheses, that's a big matrix, right? Times V, okay.
Equals A minus C times V.
Not A minus C. What's the
I
eigenvalue?
meant lambda.
Good. Lambda minus C, I'll put in parentheses, times V.
Yeah, I was just writing it down.
Oh,
I wasn't.
you got enough?
Mhm.
Okay. You do work and you try and make the ends meet. You know? I mean, when I see this, there's something very natural that comes to mind. Distribute. Right? So I'll kind of go back a step. Does that make sense? So the question is, can we get from the given to there? What would you do? Well, Tyler.
Replace the NV with the AV in the right side.
Here? You could. But I tell you what, I'm looking at what I'm given, and I'm looking at this. I have lambda v already. I kind of don't really want to.
Get rid of the CV.
Well, right, this is CV and that's CV. I mean, one way to say this is if you took the given and if you subtracted CV from both sides, wouldn't you basically be done? Almost. What's the only difference now?
The I on one side.
Yeah. So then you just have to know that V and IV are the same, and you've got a four-step proof, right? See it? I mean, when you do a proof, it's interesting. You have a statement that you're trying to prove. If you can translate it into mathematics and you can translate the given into mathematics, which is that, sometimes there's not too much left, you know? At least these exercises that they're having me do. Some theorems are much deeper than that. Multiple steps, okay? Don't get me wrong. But this is an important fact to understand. Because what does it say? It says that this thing A minus Ci, right? You could take a matrix A and you could subtract a bunch of things from the diagonal. As long as you're subtracting the same thing, you're not going to change the eigenvector. You will only change the eigenvalue, and you'll change it in a predictable way. Subtracting Ci from a matrix is the same as subtracting C from the eigenvalue. Actually, that might be very believable if I have a certain kind of matrix. So give me a matrix that you know the eigenvalues of. A 3 by 3 matrix. I don't think there are very many matrices you guys know the eigenvalues of, right? But I'll give you a hint. If I make these bottom entries 0, and let me do this. 1, 2, 3. I'll skip the 4. 5, 6, and I'll skip the 7, 8. Here, this matrix here, guys. What are the eigenvalues of that matrix? 1, 5, and 9, right? So A is the matrix 1, 5, and 9. Now what if I did A, let's do minus negative 2i, which really means, of course, A plus 2i, right? But that would be this matrix. 3, 2, 3, 0, 7, 6, 0, 0, 11, right? So what did I just do to the eigenvalues? Added 2 to each of them. This is a way of shifting the eigenvalues. And that's why it's important. The eigenvectors stay the same. The eigenvalues are shifted. Okay, so that's what problem 22 is all about. Now, when you asked me about this one, you were asking me about 23b, right? All right, I'll give it a shot. So here we go. Problem 23b says use theorem 418 and exercise 22. Now exercise 22 we just saw. I do not remember what theorem 418 is, but we'll see if we can do it anyways. Or we'll look it up if we need it. So it says find the eigenvalues. Oh, I think that theorem is just all about determinants. Find the eigenvalues and eigenspaces of, here they are, a negative 1, a minus 2i, and a plus 2i. Okay. Well, I think the easiest one for us right now. Oh, and by the way, you already did this is part B. You already did part A?
Yep.
Okay, so part A was, you had A was 3, 2, 5, 0. Can you give me the answers to part A? What are the eigenvalues? 5 and 2. And then you had to find a basis for 5 and negative 2. Okay. And so then you found a basis for E5 and a basis for E negative 2. I'm not going to do that right now. Okay. But what I'm going to say is this. A minus 2i, right? What are going to be the eigenvalues of A minus 2i? Well, they're going to be 5 minus 2 and negative 2 minus 2 by the theorem we just proved. Does that make sense? So I can say this has eigenvalues 3 and negative 4. And also by the theorem we just proved, it has to have the same eigenvectors. So that's kind of cool. The eigenvectors are the same. The eigenvalues are different.
So what is that for the eigenspaces?
Well, remember when they say eigenspaces, they're talking about infinitely many vectors, right? Usually what you do, though, is you just find a basis. You find one eigenvector. So should we do that for part A? Like E5, did you find a basis for E5? What did you find?
I got
1, 1. So a basis for E5. So I guess what should happen is that a basis for E3 is also given by 1, 1.
Okay, so
That's what should happen, right? Let's check. Here, what is A minus 2i? A minus 2i would be what matrix? Well, I guess it'd be 1 instead of 3, and this would be negative 2, right? So let's take that matrix, and let's multiply it by 1, 1, and see what we get. That gives me 3, 3, right? So, sure enough, that's 3 times 1, 1. It really works. Right? It really is. 3 is an eigenvalue with the same eigenvector that 5 had from part A. Get that? What about the other ones? Well, let's go over them while we're sitting here. A plus 2i. What are the eigenvalues going to be? Instead of being 5 and negative 2, they're going to be 7 and 0. That's interesting because that means that what? If 0 is an eigenvalue, what does that tell you about the matrix? Here, let me write down A plus 2i. A plus 2i would be this matrix. If I add 2 to it, I get 5, 2, and then what else do I get? Okay, so what do you know about this matrix? Not invertible. Lots of things, right? And I knew that because it had an eigenvalue of 0. That's always an important idea, the eigenvalue of 0. Okay, what we have not covered yet is what about A inverse? Find the eigenvalues and eigenspaces of A inverse. Well, I see two ways to do this. You either use the theorem that they've quoted or we derive it. Which do you want to do? So I have about 10 minutes.
Just use the theorem.
Okay, what's the theorem say? 418. Here's the theorem. Do you guys see what we need? Which part of the theorem do we need? Let's zoom in. We need part B, right? It says if A is invertible, then 1 over lambda is an eigenvalue of A inverse with corresponding eigenvector x. Look, x was the eigenvector. It's still going to be the eigenvector. So 1, 1 will still be the eigenvector. But the eigenvalue is going to be 1 over lambda. All right, so let's do A inverse. What would be the eigenvalues that it has?
Negative 1/5 and negative 1/2.
1/5 and negative 1/2, and they have the same eigenvectors. And by the way, this fact is also very closely related to what I did for my dissertation. So there's a reason I love this exercise. It really kind of hints at some stuff I can share with you. Probably in 2 weeks is when we're going to do this, not next week. Oh, maybe next week. Maybe the end of next week. Some of the math research I've been working on. So let's see. I think I would like to give you an exercise. I would like you to basically prove the theorem that you just used, okay? So here's an exercise, and actually, television audience at home that missed our first day after break, you guys should shut off the tape and prove this also. You'll be much better off on Thursday if you do. So here we go. The theorem is, if, how about I say this? If x is an eigenvector of A with eigenvalue lambda, and A is invertible, so that's the if, then we would say x is also an eigenvector of A inverse with eigenvalue what? 1 over lambda. I guess that's what I'd like you guys to try and prove. So I'm going to pause, let you guys get to work. I think I'll look at your homework in the meantime and then go from there. Well, I say